Perfect. So thank you so much for having me. So today I'm going to talk about algorithm as experiment. So this is an econometric method project inspired by a variety of applied domains, including market design as a key application. So this is a joint work with Kohei Yata, who is a PhD student of mine, and he will be joining Wisconsin-Madison from this fall. Then the motivation for this project is very simple and very broad. That is needless to explain to this cloud, but now it's sort of the golden age of decision-making algorithms, right? That is computational algorithms in market design and many other fields such as machine learning are now producing more and more treatment decisions and recommendations in the real world. And here are just a few of the most fashionable applications of such decision-making or resource allocation algorithms. The point of this project is to take a specific econometric look at the surge of algorithmic decision-making. That is, I'm going to claim that these algorithmic treatment decisions and recommendations produce very high-quality natural experiments or instrumental variables that are useful for doing causal inference and improving the performance of these algorithms. That is, the central claim of this project is that algorithm is natural experiment in a very broad sense. Then why is it the case that algorithm is natural experiment? So let me start with very abstract and general intuition first. So assume that some algorithm is now running to make some decision or recommendation, which I denote by Z. Okay. Then this algorithm makes this decision Z based on a bunch of input variables collected into a vector X. Then by definition or by construction, nothing else will directly influence the decision output Z other than these input variables in X, right? Because by construction or by definition, any algorithm is designed to use only a pre-specified set of input variables. Importantly, these other irrelevant variables include not just observable variables, but also any unobservable variables as well. Therefore, once we condition on X, that is, once we focus on situations or individuals with the same or similar values of X, then the decision output made by this algorithm is going to be statistically independent from anything else. In other words, this decision output Z is going to satisfy the conditional independence assumption the econometrician always wants to assume. So therefore, this decision output Z is going to work as a good instrumental variable for whatever final treatment we are interested in. The goal of this project, or the theoretical goal of this project, is to formalize and operationalize this intuition as a widely applicable treatment effect estimator. So our theoretical analysis is going to start with an identification analysis. Here, we are going to characterize exactly what causal effects we can identify when we have data generated by any given data generating algorithm. And we are going to provide an answer to this identification question for a broad class of algorithms containing both stochastic and deterministic algorithms. This identification analysis then clarifies that the data from almost every algorithm allows us to identify at least some causal effect. Then, in the main theoretical part, we are going to translate this identification insight into a specific estimator of a treatment effect. And we are going to formally prove that our treatment effect estimator is consistent and asymptotically normal for a well-defined causal effect, even in the presence of lots of heterogeneities in treatment effects. But our estimator is also easy to compute and straightforward to implement, even if the input vector X is high dimensional and the decision-making output is complex. So in general, the decision-making algorithm may contain some crazy components like deep learning or very complicated machine learning components. Even in that case, okay, the final treatment effect estimator can be made very simple. okay? And the same point can be said, okay, even if the decision-making algorithm is a complex market design one, such as the deferred acceptance algorithm or the top trading cycles algorithm. A key special case of our estimator or our econometric method is a high-dimensional regression discontinuity design. That is, in the previous conceptual framework, okay, imagine that this input X, okay, contains a bunch of running variables that jointly determine whether each person, okay, gets treated or not. Then this framework effectively nests a multi-dimensional extension of the regression discontinuity design with any number of running variables contained in X. Right? So therefore, our proposed estimator can be interpreted as a consistent and asymptotically normal estimator that can be applied to the high-dimensional RDD or regression discontinuity design with an arbitrary number of running variables. Okay? Then after developing such a treatment effect estimator, I'm going to also talk about a bunch of applications and examples. And our framework is a fairly abstract one, so that it has many potential applications. So the first group of important applications is decision-making made by machine learning algorithms. And there are a variety of different types of machine learning algorithms, starting from naive, simple supervised machine learning to more sophisticated bandit and reinforcement learning type dynamic optimization algorithms. So no matter which specific algorithm is being used for making the decision making, okay, the resulting data generated by such machine learning algorithms, okay, can be analyzed by using our method. Then on top of machine learning applications, there are many social and economic applications as well. The second group of applications, okay, is related to market design and centralized mechanism design. So I'm going to talk more about this point, but think about auction algorithms or matching and assignment algorithms. At a very high level, these market design algorithms are just particular examples of decision-making algorithms that use some observable information to make some decision or resource allocation, right? So in that sense, the data coming from market design can also be analyzed by using our data. And I'm going to talk about a particular application using data coming from the school choice matching mechanism, okay, as a first sort of application coming from a prior joint study of mine. Then the final group of applications is related to public policy eligibility rules. So think about, say, a particular policy domain like Medicaid in the US, okay, or many other similar policy domains with resource constraints. So in such policy domains, okay, the government often uses some algorithmic rule, okay, and observable characteristics of individuals or households to determine who are eligible for that policy, right? That is, whether a particular individual in the US is eligible for Medicaid or not is determined by a particular sort of rule or formula or algorithm, okay, applied to observable characteristics such as the income level and the family composition and so on, okay? Then these policy eligibility rules can also be taught as decision-making algorithms. So therefore, the data coming from such policy eligibility rules are additional examples of our framework. And as a particular original applications in that spirit, I'm going to use our method to evaluate the effect of hospital relief funding distributed by the US government during the COVID-19 pandemic. And this policy distributed hundreds of billions of dollars, okay, to struggling hospitals to help their efforts to deal with COVID-19 patients. And the US government used some a particular algorithmic funding eligibility rule so that the resulting data can be analyzed by our method. And we are going to use our method to find that this hospital relief funding probably had very limited or effectively no impact on any hospital activities related to COVID-19, such as the number of COVID-19 patients accommodated by hospitals or the COVID-19 related mortality rate and so on. So our empirical bottom line is that probably this hospital relief funding made by the US government was close to a waste of money from the perspective of this particular policy. So I'm going to talk about both some theoretical development as well as empirical applications. But is there any comments or questions at this point? Great. So then let me jump into our framework. So our framework is a fairly simple econometric framework for estimating the causal effect of a particular treatment on outcome. So imagine that there are a bunch of individuals indexed by I, okay? So each individual I, okay, has a vector of fixed covariates denoted by xi, okay, which has p components. The support of this covariate vector, okay, is going to be denoted by this calligraphy x, okay? Then each individual I with these covariates xi is going to first receive some treatment recommendation, which I denote by zi, okay? For simplicity, this treatment recommendation zi is assumed to be binary, okay? Then the most crucial assumption made here is that this binary treatment recommendation is assumed to be made by some known algorithm, which I denote by this A, okay? Then this A is just an algorithm or function, okay, that maps each possible covariate value in this covariate space, okay, into the unit interval, okay? The interpretation here is that the output of this algorithm or the function A is the conditional probability of a treatment recommendation when individual I has a particular covariate vector value, okay? Then the important point is that this algorithm A, okay, may be either stochastic or deterministic. That is, the output of this function A may be either 0 or 1, so that this can be a deterministic function, okay? So this binary treatment recommendation Zi is assumed to be made by a known algorithm that may be either stochastic or deterministic. Then after that, each individual is going to receive a final treatment assignment, which I denote by Di, okay? Then if I use this Di of Z to denote the potential or hypothetical value of this treatment assignment, when individual I's treatment recommendation is fixed to a particular value, small z, okay, I can write this final treatment assignment in this way, which is familiar to those who know a lot about econometrics. Okay, then finally, each person is going to generate some outcome, which I denote by yi. Okay, and again, if I use this yi of d to denote the potential outcome, when individual i's treatment assignment is being fixed to a particular value, small d, then this observed outcome can be written in this way. That is, when individual I gets treated, okay, we are going to observe this y of 1. And when the individual I isn't treated, then the observed outcome is going to be this potential outcome, okay, without any treatment. Okay, then for those who are familiar with this kind of causal inference framework, this is a very standard framework of causal inference with instrumental variable and observable covariates. The only departure from the standard setting is this highlighted part. That is this treatment recommendation Z, okay, or the instrumental variable Z, okay, is being assumed to be made by a known algorithm. And this twist makes this setup interesting and tractable, as I'm going to show in the next 10 minutes. Okay, any questions about this model and the framework?
Yes, can I please ask a question? Yeah, this is Andre speaking. So my question here is that, do you really assume that X is independent of DI? Am I correct?
That X is independent from DI. So X is assumed to be fixed and given. So in that sense, this X is a deterministic object so that it's independent from anything else.
In that sense, X might be used as an instrument itself.
Another related point is that this Xi changes the distribution of this binary treatment recommendation Zi. And this Zi treatment recommendation may be systematically related to this treatment assignment. So in that sense, there is some sort of connection or link between Xi and Di.
Thank you.
Yes, great. Any other questions about the framework? Great. So then to make some progress, I need just a few regularity conditions or assumptions. The most crucial assumption or property, okay, is the following conditional independence property. That is, this algorithm A makes its treatment recommendation Zi only based on these observable characteristics or input variables Xi. So therefore, conditional on Xi, that is, among individuals with the same values of Xi, okay, whether each person gets treatment recommendation or not is independent from anything else. In particular, potential outcomes Y1 and Y0, and the potential treatment assignments D1 and D0. Okay, then I'm going to assume this conditional independence property throughout, and note that this conditional independence property, okay, is not really an assumption, but rather a true property or fact guaranteed by the construction of the algorithm in many applications. Then I also need to assume a few, okay, regularity conditions. The only substantive regularity condition is this first one. That is, this algorithm A, function A, must be continuous almost everywhere. So this may involve finitely many discontinuous points, but almost everywhere it must be continuous. Okay. Then only for this presentation, just for simplicity, we assume that this Xi vector contains only continuous components, and the paper extends the entire analysis to the case, okay, with discrete components Nx. But this continuous X makes the notation and the representation much simpler. Okay, so then to connect this framework, okay, to sort of something which you already know, let me sort of explain a few important special cases or examples of this framework, just to make sure that everybody is on the same page. So one of the simplest special cases of this framework, okay, is probably a stratified RCT or selection on observable or the propensity score scenario. That is, imagine that this algorithm A, okay, or the treatment recommendation probability made by this algorithm, it's strictly between 0 and 1 for every possible value of X. Then this effectively means that everybody is facing some explicit randomization or stochastic treatment recommendation, okay, in a way that uses only the information about X. Then this is effectively a stratified experiment, okay, where treatment assignment probabilities may be different across different individuals with different covariate values. So this is a very simple setup or special case, and we know what to do in this special case. But this framework also contains many other interesting scenarios. For example, another example is the regression discontinuity design. So imagine or assume that, okay, this input vector X contains only a scalar running variable. Okay, then conditional on any value of this scalar running variable, okay, the treatment recommendation probability is either 0 or 1, so that it's degenerate. Okay, but as we move across different values of the running variable, okay, this treatment recommendation probability jumps from 0 to 1 or 1 to 0. Then this is a familiar regression discontinuity design, okay, where the treatment assignment is sort of deterministic, but depends only on this scalar running variable. So in this sense, our framework is an integration of the first stratified RCT example and the regression discontinuity design. And because of this integration, this framework contains many other complicated scenarios, such as machine learning algorithms and market design algorithms under high-dimensional RDT. Okay? And there's no established or standard estimator, okay, for this most general setup with imperfect compliance, okay, and the no overlap condition or the violations of the full support condition. So our methodological goal is to provide a widely sort of easy to use estimator that can be applied to any example in our most general framework. Okay. Then before sort of showing our estimator proposal, let me also explain how sort of this framework is related to market design. So here is sort of how matching and auction, okay, can be nested into our framework. So let's first think about the case of matching or assignment. So in this case, okay, in so school choice analogy, individuals I correspond to, say, students or families participating into the school choice matching algorithm. Okay, then sort of each student has a bunch of pieces of observable information, such as the preference of order over schools and the priority status at each school, and maybe some tiebreaker like test scores or lottery numbers, right? The vector of all of these input informations used by the mechanism is X, okay? Then some known algorithm or mechanism, maybe deferred acceptance, maybe top trading cycles, or maybe immediate acceptance algorithm, determines whether each student I is assigned to a particular school or the treatment school. Then this assignment variable corresponds to our Z. Then we may be interested in, okay, the effect of attending the treatment school DI on students' future test scores. So this is a particular way, okay, a matching algorithm can fit into our framework. Then auction is also a possible example of our framework. There are a bunch of bidders that correspond to individual I in our framework. Okay, then each bidder has an observable bit contained in the data, maybe along with some additional characteristics that matter for the final allocation. Then the given auction algorithm determines, okay, which bidder wins the good at which price. So that sort of auction outcome is our Z variable. Okay, then we may be interested in the effect of this auction outcome on bidders' future economic performance. So in this sense, market design algorithms can also be taught as examples of our framework. Okay. Yes, go ahead.
Hi, it's Kemi. I have a quick question. Do I understand correctly that the value added of your approach is when there isn't full compliance between Z and D? That your approach is particularly relevant in this environment?
So that environment with perfect compliance is a particularly easy example of our framework. But our method can be used even if this Z and D are completely different from each other. So in many school choice applications, many students students' enrollment outcomes often deviate from their assignment outcomes. So in that case, this Z and D is going to be different from each other. So our method can be used in that setup as well. But if there is perfect compliance, it will be easier. Yes. Okay, so then our goal is to provide a method to estimate the effect of D on Y. Okay, and here is the proposal in a single slide. So if you are an empirical researcher, so this slide is the only thing you should remember at the end of this presentation, okay? Then our goal or our question is the following one, that is, suppose that we have a sort of finite sample or data set generated by the previous framework with some known algorithm A. Then how should we use this data to estimate the effect of the treatment assignment D on the final outcome Y? Here is our proposal. Our proposal is the following two-step estimator. The first step, okay, is an intermediate simulation step. Let's pick some small bandwidth value delta, okay, as well as a large integer s as the number of simulations. Okay, so these are some design parameters picked by the analyst and the econometrician. Then, given these two values, okay, we are going to first simulate these objects x star 1 to x star s. And these are, okay, a bunch of independent draws from the uniform distribution over the p-dimensional delta ball around individual i's covariate. That is, in the covariate space, each individual I has a particular covariate point, right? Then let's think about a small ball or neighborhood around that covariate point. Okay? Then we consider the uniform distribution over that ball, which I denote by this capital B. Okay? Then let's draw a bunch of sort of independent covariate values from that uniform distribution over the neighborhood. That's what these X star objects try to denote. Okay? Then let's substitute each simulated covariate value, okay, into this algorithm A. Then this is going to produce some associated treatment recommendation probability, right? And let's compute that treatment recommendation probability, okay, and take the empirical average over many simulations, capital S simulation dollars. Okay, the final average is gonna what I'm gonna denote by this blue object, P of X delta. Okay, then this object is effectively a sort of simulation approximation to the approximate value of the treatment recommendation probability, okay, in a small neighborhood around individual i's covariate value, right? And I'm gonna call this object the approximate propensity score in the paper, or APS in short. Okay, then this treatment effect estimator, okay, then combines this first step simulation object or the approximate propensity score, okay, with the familiar two-stage least square instrumental variable regression. That is, at the end of the day, we are interested in how this outcome yi, okay, is impacted by this treatment assignment di, right? But of course, this treatment assignment is far from randomly assigned, okay? So that we need to find some instrumental variable for treatment assignment. Our proposed instrument is this zi, which is the outcome of our algorithm A. Okay? Then to make this algorithm out of zi a good instrumental variable, we need to control for some appropriate object to make this z, okay, conditionally randomly assigned. Our proposed control, okay, is this one. That is, we propose to linearly control for the approximate propensity score coming from the first step simulation. Okay, then our final estimator, okay, is this beta object. That is, this is the two-stage least square estimator coming from this specification, linearly controlling for the propensity score. So our main theoretical result, okay, is that this beta estimator coming from this two-step procedure is consistent and asymptotically normal for a well-defined causal effect, even in the presence of treatment effect heterogeneities. So in this sense, okay, this algorithm A may take a variety of different forms. This may be deferred acceptance. This may be some combinatorial options. This may be some crazy machine learning algorithm. But what we should do at the end of the day, okay, is to blindly apply this two-step procedure, okay, without worrying too much about the details of the definition of the decision-making algorithm. So no matter which specific algorithm is being used, this beta estimator is kind of good enough. Any questions about this definition of our treatment effect estimator?
Yes, can I clarify?
Andre and Peter, yes, go ahead.
So actually, I'm coming back to my previous question. Do I understand correct that z is a function of x in this specification in the last equation, right?
That's right.
So it means that you are using nonlinearity in your specification, and this nonlinearity identifies the beta. Because if we assume that this probability APS is linear function of x, and z is also a linear function of x, then there is no identification anymore. So it's like
why is that?
Because let's consider a very simple example of Heckman selection model.
Yes.
And let's assume that we have no other additional variable in both first stage and the second stage, and we use the same variables in both equations. And the Heckman selection model identifies the parameter only because we use non-linearity of the probability model in the first stage.
But unlike the Heckman selection model, here sort of this P term, this part, it is in a sense a known thing. That is, we know this blue part from the first step simulation, right? And we don't need to estimate this blue part, so that we don't need to worry about the kind of the independence or the lack of dependence between this Z part and this P part. So since we know this P function from the first step simulation, even if this Z variable is a linear function of Xi, I think this two-stage least square regression is going to go through.
So even if the function APS is also linear, so if the APS function is linear, and Z is also linear, will it work?
That doesn't matter, because this P is some known function. We don't need to estimate it, so that we don't need to care about sort of the identification or the estimation of this P part. That's the key, I think. So in this sense, this framework is really sort of using the assumption that we know the algorithm and we know this approximate propensity score P from the first step simulation.
Thank you.
Yes.
So I'm wondering if you could help me with an example, just
Sure.
so to clarify things in my head. So let's say we have an auction, then the algorithm are the market rules that map the bids into outcomes. And my question is the interpretation of why. So typically in an auction, what we'd be interested in is how the market rules impacted revenues to the seller, or the efficiency of the outcome. Is that the correct interpretation, or did you have something else in mind for why?
Yeah, so the typical sort of candidate for why in an auction example is some sort of future economic performance or future business KPI or beta I, right? So in a sort of existing empirical paper, some marketing folks sort of looked at data coming from online advertisement auctions done by Google and Yahoo and so on. And they analyzed sort of whether winning an advertisement auction really sort of improved their advertisement sort of revenue bottom lines, say weeks after the auction. So that's the typical choice of this outcome. Why?
I see. So it's distinct from the standard question
very
auction
different
design.
from that.
Yeah,
that's right.
yeah.
So this is very different from
yeah,
the.
it needs to be bidder specific. Some impact on the bidder going forward. Okay, good. Thank you. That's very helpful.
Yes. Any other questions?
Yes, hi Yusuke. So I have a kind of symmetric question to Peter in matching now. So, if I think about school choice or most of school choice applications, usually there are a lot of rounds that go beyond the algorithm, because some people will refuse some seats, and then there would be additional rounds of match that are usually administrative and not done by the algorithm itself. And so I was wondering to which extent could it be a threat to this method? Because on one extreme, I could think that the algorithm has no impact and there is only a committee that is deciding of something, which would be one extreme of how the Z is completely different from the D, I would guess. So then I was wondering what if there is this kind of additional steps that are administrative assignment, or should I be worried about the method or not?
Right. So such additional steps or administrative adjustments are going to generate some discrepancy between Z and D. that is a treatment recommendation, versus the treatment assignment. And the discrepancy between Z and D is gonna make the final estimator less statistically efficient and less precise than we would hope. But the entire framework, so the basic framework of our method, it's going to be valid, sort of no matter how many additional steps are there and how many additional compromises there are to the connection between Z and D. Okay. But if this Z has really no influence on the final sort of treatment assignment D, then the data coming from the matching mechanism is going to be effectively useless.
Thank you.
So I have a question.
Yes.
It's related to the matching application. So in this application, usually the covariates are discrete. The preferences are discrete. And the characteristics are usually number of siblings in the same school.
Right.
And so here, if I understand well, you're assuming that there is some Euclidean structure on the covariates. So there is a...
That's right. So we need to have some continuous covariates. And in the case of matching or school choice application, such continuous covariates are typically test scores or lottery numbers or something like that. So we need to have some continuous covariates. That's right.
Okay.
So it may help to explain a particular market design application then. So one possible application of our method is that to data coming from school choice matching mechanism. And in a prior sort of application, we are looking at whether sort of attending selective elite schools are really beneficial for students or not. And we did this analysis sort of motivated by some policy discussion about the inequality in access to elite schools in New York City. So this is a sort of old or prior application I did with Attila and Josh and Parag in our now published papers. And in this empirical application, we estimated the effects of attending elite schools compared to ordinary schools by using data coming from New York City's deferred acceptance algorithm. And this setup corresponds to our framework in this way, which is very similar to what I explained before. And your question is related to this algorithm input, I think. And this Xi, of course, contains student I's preference order over the schools, as well as each student's priority status at each school. Okay, but on top of this, New York City uses both test score tiebreakers as well as lottery number tiebreakers. So this Xi contains all of these things, and test scores and lottery numbers are continuous input variables that produces real quasi-experimental variation. Okay, and here, so we are interested in a particular group of elite schools called grade A schools in New York City, which contains many of the most selective schools in New York City's sort of main high school choice system. Then we are interested in whether attending any one of these grade A elite schools, this one, affects each student's future test scores and other outcomes. Then to do that, we are going to use the assignment made by the deferred acceptance algorithm as our Z, which creates some quasi-experimental variation in the final treatment. Okay. Then the bottom line of this empirical application is that these elite schools appear to have little to no causal effects on students' future outcomes. To do that, we looked at three important outcomes. So SAT math test score around the graduation points from these high schools, SAT reading test score, and finally, high school graduation outcome. Okay, then for each one of these outcomes as our Y, okay, we use the slightly modified version of the previous estimator to estimate the effect of attending a grade A school on that outcome. Then the starting benchmark is this blue bar. So for each outcome, this big blue bar, it's the simple comparison or simple difference between grade A schools versus other schools. That is, so without controlling for anything else and without using our method. Okay, so then this means that this suggests that these blue bars say that grade A schools are, of course, okay, are much better than other schools in terms of any one of these outcomes. Okay, students at grade A schools tend to have much higher SAT scores, and the students at grade A schools are more likely to graduate from high schools. So no surprise, and this is just a sanity check. Then the final bottom line is this gray bar. Okay, so this gray bar is our two-stage least square estimates, okay, using the instrumental variable or the quasi-experimental variation generated by lottery numbers, okay, as well as test score tiebreakers. And once we incorporate this natural experiment in a precise way, okay, then these gray bars look much shorter than blue bars and very close to zero. Then this means that probably the original apparent difference between grade A schools versus other schools, okay, shown in blue bars, is driven mostly by selection bias instead of a true causal effect. Okay, and these gray bars show that the real causal effect of attending grade A schools on these outcomes is probably very close to zero, at least according to the specific quasi-experimental variation we can exploit. Okay, so then this is one way we can use our method to estimate, okay, the effect of school attendance by using market design data. Then the next final application is an original new application that also clarifies the power of our method in a completely separate domain. So this empirical application is about the so-called CARES Act, which is an abbreviation for the Coronavirus Aid, Relief, and Economic Security Act. And this is probably one of the biggest economic stimulus package in the entire US history. And this act distributed hundreds of billions of dollars in relief funding to hospitals to deal with COVID-19 patients. And the policy goal was to simply sort of help financially insecure hospitals because they may be less capable of investing in COVID-19 response efforts. Then the goal or the research question in this empirical application, okay, is whether this problem was really alleviated by this hospital funding or not. That is, what was the real effect of hospital funding on COVID-19 related hospital outcomes. To do that, we are going to use the following institutional sort of feature. That is, in this policy, okay, whether each hospital is eligible for getting this funding or not was determined by an algorithmic rule applied to 3 hospital characteristics. So this is not an health economics seminar, so you don't need to understand the exact definition of each characteristic, but effectively these 3 conditions, okay, about 3 particular hospital characteristics, okay, are pinned down whether each acute care hospital was eligible for this policy or not. And the intention behind this rule was to simply target hospitals, okay, that provide care to the most vulnerable part of the population and operate on thin margins. Then a visual version of this funding eligibility rule is shown here. So let's take a look at this 3D space. Okay, this 3D space is spanned by the 3 hospital characteristics that jointly determine funding eligibility, okay, such as the profit margin. Okay, then dots or marks in this 3D space are hospitals in our data. Okay, then red circles correspond to eligible hospitals, while blue marks correspond to ineligible hospitals. Okay, then from this 3D picture alone, it's hard to see what's really going on. So let's extract a couple of 2D planes from this original space. Something like this. So each plane, okay, focuses on 2 out of the 3 hospital characteristics determining funding eligibility. Then as you can see in each 2D plane, okay, there is some sort of discontinuity, okay, in the determinants of funding eligibility, right? That is in this plane, okay, this boundary, okay, dramatically changes whether hospitals are eligible or not. And in this plane, okay, a similar boundary is here. So this means that the original 3D space is a collection of infinitely many, okay, such 2D regression discontinuity design or boundary discontinuity designs. And our framework provides an automated way to extract all of the instrumental variables or quasi-experimental variation embedded in this 3D space. Okay, so we used our method to estimate the effect of the amount of funding on the COVID-19 related outcome. So here, okay, the 3 eligibility determinants correspond to that vector of input variables, xi, in the theoretical framework. Then this x determines whether each hospital is funding eligible or not, which is our z. Then our treatment is this d, which is the amount of funding each hospital gets, okay? And we are going to estimate the effect of this funding amount on the number of COVID-19 related patients accommodated by hospital I. Okay, then here is the main empirical result. So naively speaking, okay, looks like this funding policy appears to have some positive and significant sort of effect on this COVID-19 outcome. For example, if we use simple OLS regression, okay, that simply compares eligible versus ineligible hospitals, or if we use naive two-stage least square regression without that approximate propensity score control, okay, then we find, okay, a highly statistically significant and economically significant effect of funding on the number of COVID-19 patients. Okay, for each $1 million of funding, okay, the average hospital gets about sort of 3 to 5 more COVID-19 patients, okay, in the hospital, okay. But once we control for the approximate propensity score, according to our theoretical framework, then all of these significant stars go away, and the estimate of the effect of funding on the number of COVID-19 patients becomes even negative. Then this suggests that probably the original significant sort of effect of funding on the number of COVID-19 patients is probably due to selection bias, mostly speaking. And the real causal effect of this funding is probably pretty close to zero. And the same result, even for the number of patients in ICU, and the same result even several months after the distribution of this funding. So here, the horizontal axis is time, and the vertical axis is the estimated effect of funding on the number of COVID-19 patients at each point in time. Then across the board, the estimated effect from our method, blue line, is around 0.0 and is never significantly different from 0. So in this sense, our analysis provides some sort of causal support for the widespread media concern. Okay, a lot of people talked about sort of at the start of this policy. That is, a lot of people sort of thought that this funding algorithm was not very well targeted. Okay, and the hospital funding sort of was taught to go to hospitals that don't really need funding, or hospitals that are so financially poor that they cannot sort of use that funding to build up sort of enough equipment to deal with COVID-19 patients. So in this sense, sort of our analysis suggests that the media concern back then was a correct and precise one, and the funding algorithm used by the government should have been better designed. But I'm running out of time, so let me wrap up and summarize what I talked about. So the simple takeaway from this project is that now sort of algorithms in many domains are sort of taking over the world in several senses. And as sort of algorithm is the world becomes a mountain of natural experiments and instruments. Then the question is how to analyze, such algorithm-produced natural experiments for doing correct causal inference. And we provide a simple but general method that combines the simple two-stage least square instrumental variable regression with the so-called approximate propensity score concept. And we provide some theoretical justification or theorem as well as empirical applications. But that's it for now. So thank you so much for your time and questions. And I'd be happy to engage in any additional discussions.
Thank you very much, Yusuke. Thanks a lot for the talk. It was great. Before to keep going, let me announce the next talk, which is in 2 weeks on the 14th of March. We will welcome Matt Elliott from Cambridge University to talk about market segmentation through information. So we have a lot of time, so feel all free to ask your questions and keep going.
So maybe I have one question to, so you talked about machine learning algorithm that makes recommendation. So I was curious to know, so usually it's hard to, I mean, except if you are the recommender yourself, it's hard to have access to the exact algorithm that they have been using, or the algorithm was parameterized and so on. So I was wondering, can we kind of, if we have some assumptions that we can approximately estimate what is the A function, can we, like, let's say we learn what is the machine learning algorithm, can we use your technique afterwards in some sense? And if yes, then it asks also the question, if we have a committee of people who are taking decisions, and then we can learn an algorithm to reproduce very precisely the outcome of this committee, could we use also your same technique from this algorithm to try to simulate causal effect on this committee, for instance? On some assumptions and precisions, obviously. I mean, if they have some implicit rules that we don't know, but they are explicit to them, then we can learn what are these rules based on observables, and then try to use your technique. So do you think this would be feasible?
Yes, that will be probably feasible, or hopefully feasible. So you are correct that in most machine learning applications, so the outside analyst doesn't really know exactly what algorithm was being used for creating that data. So in that setup, we would need to sort of estimate what algorithm was used. So we are sort of currently trying to expand this framework to the case where the algorithm is unknown, and maybe sort of satisfied some shape restrictions and so on. And the analyst needs to sort of estimate that algorithm component A. And how to do that. So that's a little sort of tricky question from the theoretical perspective. So we are currently working on that sort of problem. So stay tuned, and then I'm hoping to sort of come back here to report our progress along that line.
Thanks.